All right, period 8. Welcome. You are going to watch a video of a really important topic. So important, the new marker is going to be used.
Oh.
And I think I'm going to skip this long-winded introduction. I think we're just going to go right for it. So maybe I have to give the long-winded introduction. Okay, maybe I'll give long-winded introduction. So check it out. This next 5 minutes is a preview of logic math, the best class at Blair High School and possibly the world, which you should all take when you're seniors. And in that class, we learn all about the history of math, and particularly about attempts to axiomatize certain branches of mathematics. And it was in the late 19th century that people actually tried to come up with axioms for arithmetic. And so let's particularly talk about the natural numbers. So, well, what are the natural numbers? That's like, you know.
1, 2.
Yeah, except we basically put 0 in there also.
Please.
So, yeah. So it's like this. I know there's this like whole number thing. That's just propaganda that they teach in middle school. There's no such thing as a whole number except in middle school math teacher lingo. In the real world, you talk about the natural numbers. We always put 0 in there because it's nice to like have 0. It's kind of important. Anyway, there's controversy. You can like Google it. You know, there's some minority of mathematicians who don't want to put 0 in there, but basically everyone puts 0.
Oh, you mean Giles?
There is this set, of course, but Eric, this set also has some like structure to it, right? Like what? Okay. You're on video, so you gotta say something. You don't even know what I'm talking about. What are the relationships between these numbers? Yes? Yeah, they increase by 1. In particular, like some of them are bigger than the others. It's not just like a big jumbled set of like numbers, right? Then it wouldn't be too useful. They increase by 1 each time. In fact, there's some kind of like order between them, right? And then it sort of goes kind of in order. Okay, so somewhere around the 19th century, somebody realized that actually the best way to talk about the numbers is to say that they're related to each other via this thing called the successor function. So, like the successor of the number 3 is 4, etc. Okay, so armed with this idea of a successor function, let's just imagine that some hyper-intelligent alien was beamed down from outer space, and suppose he came up to one of you, which would be really lucky because we've already had this conversation. You'll know what to say. And you started talking about math because that's the universal language. Next thing you know, you realize that this guy doesn't know that much math. What he does know is he's in fact he's very smart. Obviously, he made it to our planet before we made it to his. So he's very, very smart. But he doesn't know what numbers are.
So he knows math, but he doesn't know what a number is.
He knows a certain kind of math. He knows about like structures and like relationships, and he knows like what functions are. And he's also a perfect logician. So he can like, once you tell him the sufficient amount of information, he can like reason appropriately. He just doesn't know what these, we keep talking about numbers. He's like, wait, what numbers? What are numbers? All right, so how are you going to explain what numbers are to a guy who's never heard of numbers, but does understand like math in a certain sense? Yeah, say something.
So you say, take a graph, because they know functions, right?
Okay.
So
I cut you off. You are wrong.
take a graph, and then put lines that are equidistant from each other, going up.
Okay. I see where this is going. Yeah.
So if we're talking about natural numbers,
That's what we're talking about. Specifically,
then
natural numbers.
You can talk about how it's quantities of things.
Okay, so that's good and stuff. If he was like a baby alien, and you were trying to like get him to make it really nice, like it's like if you have like 2 aliens, that's like 2. But no. We're just going right. Just go right for it. Like there's no need to. Like we just go right for it, right? Like tell him like you can express it like in complicated formations. But actually, it doesn't have to be that complicated. Just tell me something about the natural numbers. They're all one. They're all one apart from each other. Yeah. What else? He doesn't know anything about this set whatsoever. Caleb, you can also probably like sit down because Julian can't speak. Just tell me like one thing about this set. Oh. Okay, so let me I'll take what Cindy said. Cindy says they're all one apart from each other. In other words, one way, once I've introduced you to the concept of a successor function, one way to express that would be to kind of say, what? What is it about the numbers? It's not just that they're one apart, but whenever you have a number,
It has a successor.
it has a successor, right? So yeah, so that's kind of like an interesting idea, right? One thing you could tell the alien is, okay, well, there are these things called numbers. Meanwhile, the alien has no idea what you're talking about, right? But you might say, well, it's kind of like when you have a number, there's always like a next one. This kind of seems like a way of explaining how numbers work. Yeah, so we could say something like, well, if you have a number, then the successor of that number is also a natural number. You guys understand that sentence? Seems good. Seems like an important fact about numbers, that there's always a next one. They don't stop. Well, okay, what else? Tell me something else. Besides the fact that they don't stop. It's a hard lesson. It's being taped on video forever. Yeah, besides the fact that they, and I'm going to try to help you by giving you heavy hints here, that not only do they not stop, but they also start somewhere, okay? So there are some numbers. For example, Dawson, what's one number?
0.
Yeah, the 0. Yeah, that seems like a good place to start. If you were trying to explain to the alien what the natural numbers are, you might start by saying, well, first off, there's this number called 0. So now the alien is thinking, oh, okay, I think I get it now. All right, so there's this number you guys call 0 for some strange reason. It looks like, I don't know, the sun, which seems to be important to you Earthlings. So there's this number called 0, and whenever you have a number, the successor of that number is also a number. Okay, so now the alien kind of stops you for a minute and says, all right, let me make sure I see if I understand this. So there's this number called 0, and then the successor of that, I'll just draw an arrow from a number to its successor. So the successor of 0 is just like 0, right? Great, this is a great set of numbers that you have. There's just one of them and everything's great. Then what are you supposed to say to the alien? No, stupid alien. You got it all wrong. And then the alien is going to respond, well, look, man, I only know what you tell me, so you need to tell me some more things. Tell me some more things.
Different numbers.
Mateo.
Numbers don't repeat.
The numbers don't repeat. That's a little bit hard to express that, though, right? Okay, keep going. More people, yeah.
Each element of the set is unique.
Each element of it is, well, there's still a unique number. It's just that the successor function thinks that the alien thinks that the successor of 0 is just 0
The
again.
successor function leads to a different number.
Yeah. So one way of saying that is to say that how can we is now you guys being like math? Yeah. Okay. Yeah, that's actually an idea. He says that S of n is not n. In other words, Will says that the successor of a number can't be that number. That seems like a good axiom. Do you agree? Okay, good. So then Elaine says, okay, I get it now. I get it now. So the successor of 1 must be some new number, because it can't be 0. So I guess I'll just call it successor of 0, although we might decide to nickname it 1. And then the successor of 0 is back to 1 again. Yes, I got it.
No.
No, dumb alien, no, you're wrong. Okay, what next? We have to keep giving him more information, otherwise he can't understand the natural numbers.
You cannot repeat any numbers that have been previously used.
Okay, how can we explain that? Yeah. Okay, but I don't know what greater than means, so, In fact, we're going to define greater than in terms of the successor function. How do you say the numbers don't repeat? What property does the successor function have? Yes? Yes?
It's 1 to 1.
Yes! Good! Good. I nominate Eleanor to speak to aliens. Eleanor says the successor function is 1 to 1. The successor function is 1 to 1. And the classic way to write that a function is 1 to 1, when you want to write that a function is 1 to 1, what you want to say is that if you have two numbers, x and y, which both go to z, That's what's like not allowed, right? When if you want a function to be one-to-one, you have to somehow like exclude this situation, right? How can I write a sentence which excludes two different numbers both pointing to the same number? Well, here's how you do it. You can say, if you give me two numbers, and the successor of x equals the successor of y, then what?
Then they're the same number.
Then they are the same number. Yes. This is the quantifier logic conditional kind of representation of saying that if two numbers have the same output, then they must be the same number. That captures what we mean by one-to-one. I don't know if you guys did some JAWS last year, but in functions, I talk about this as a way of saying that a function is one-to-one. If you think that over, it kind of makes sense. Okay, now we know that the function is one-to-one. So now have we given the alien enough information?
Yeah.
Oh, by the way, do I need to? Okay, let's see. Well, okay, 0 goes to 1. Let's just call this 1. Should we call this 1? Okay. And now the alien says, all right, well, 1. Actually, can 1 go to 0?
No.
Why not? Is this function one-to-one?
Yeah.
Yeah, I think it is. 0 goes to 1, and 1 goes to 0. Uh-oh.
Not if you like have it be like a loop kind of, but like
I think we have to tell him something else.
Tell him that all the numbers have to be different. Just tell
The-
him. Just tell him that.
No, he doesn't understand these
Wait, what do
vague
you mean?
concepts. He's like a logician.
Wait, does
You
he,
need to
like-
give him the formal. What do you mean by different? They are different. There's
Does
0 and
he-
1. They're both different.
does he get
What are you talking about?
Does he get
You
like
can't
slope,
have
like,
the same
you have
number.
to-
Like a number
No.
can't show up in the thing twice.
Can't show up in the thing twice. Okay, here. What you guys are missing is
Multiplication.
there's something special about 0. What's special about 0?
It's a start.
It's nothing's successor.
It's nothing's successor. Yeah, you better tell me something about 0. There is something very, very important about 0, which is 0 is like the beginning, right? So here's a very important axiom. 0 is not the successor of any number. Okay, now I think we're basically done.
No, because then he's just gonna be like 0, 1.
Well, let's check it
2,
out.
and go back to 1.
Well, I don't know. Is that possible? Let's find out. So we start with 0. Okay, we start with 0. And 0. Okay, so now what's the successor of 0? Well, it can't be 0. Successor of 0 can't be 0 because we have an axiom, axiom 5, which says that 0 doesn't have a successor. That means I must have another number. And so the successor of 0 must be 1, right? Okay, and now what's the successor of 1? Well, it can't be 0 because we have something that says that nothing points to 0. Could it be 1?
No.
No.
No, because why not?
Because S of n does not equal n.
Yeah, actually, I don't even think we need this one anymore because this is captured by Eleanor's suggestion that the function is one-to-one, right? This can't be because then 0 and 1 would both be pointing to the same thing. Do you guys see that? And 0 and 1 can't both point to the same number because they're different numbers. So 1 can point to 0 and it can't point to 1, then it must point to some new number, which we might nickname 2. Okay, what's the successor of 2? Could it be 0?
No.
Because then you would have, because 0 can't be the successor of anything. Could the successor of 2 be 1?
No, then 2 would have to equal 0.
Yeah, because 2 and you can't have 2 and 0 both pointing to 1. Could it be 2?
No.
Because then you'd have 1 and 2 both pointing to the same number, so that's not allowed either. Okay, so in the pure language of mathematics, okay, so I'm sort of forced to include a new number. So I think, Rohan, I think we've succeeded. I think these 4 axioms together determine that there must be, in fact, some infinite sequence of numbers in some sort of relationship. Okay, so this is a kind of advanced and very abstract. This is a property that the natural numbers have. All right, unfortunately, you might think that we're done.
We're not.
Problem is we're not done. Because this alien says, okay, I think I understand. But then the alien might think, well, this, so there's this spectrum, so that's good and everything. But then there is a whole nother chain of like evil 0 and evil 1, right? So,
what?
watch. I'll put like, rah. So that's evil 0, and then the successor of evil 0 is evil 1. And
What even?
and the successor of evil 1 is evil 2. And the successor of evil 2 is evil 3. Leroy's kind of happy actually. Okay, does this violate any of my axioms? Hey Lowell, no, I don't need a lunch, but thank you.
I do.
Hi, Michelle.
Okay, does every number have a successor?
Uh,
Yeah, is 0 is a number. Is this function 1 to 1? Yeah. Is it the case that 0 is not the successor of any number? Uh-oh.
Wait.
Kind of a problem with
Well,
our
why did you say-
axiomatization. This is a very advanced concept, and if we don't get it, I sort of don't care that much. But
Can't you just
But
tell them that
what's-
they can't be evil?
yeah. Okay. So the problem is that these four. This is a very subtle concept, and then I want to move on. I'm regretting doing this at all, actually, at this moment. These first four axioms determine that there must be numbers like this, but they don't exclude other things that might be there. For example, there could just be like a monster. And this monster might have a successor. And yeah, that looks pretty good. And this monster might have him as a successor, and then he might be his successor.
What? I'm really confused.
Do these four axioms exclude this situation? I think that they just don't, right? Because every number has a successor. The successor of this monster is this monster. 0 is a number. The successor function is 1 to 1. It is 1 to 1. And no one has a successor of 0. So the problem is that this axiom system is not quite complete. Because the whole point of an axiomatization is that you should be able to explain to an alien the properties, and then the alien should be thinking the exact same thing that you're thinking. You guys feel like you kind of get this? Alright. Alright, so it turns out that we need another axiom for the natural numbers. And this axiom is not obvious at all. And this axiom needs to say something like, well what, maybe you should tell me. Roughly, yeah, Nikili? Is that a hand? No. This axiom needs to say something like, these are the important ones, or something. The axiom system needs to say, it's the numbers which are successors of 0 which are numbers and nothing else. What we want is this fifth axiom to exclude cases in which there are like other crap floating around. Okay, and this axiom system is called the principle of mathematical induction. The principle of mathematical induction. And the principle of mathematical induction says something very complicated. It says that if something is true of 0, and it's true, whenever it's true for a number, it's true for the successor of that number, then it must be true for all numbers. And writing this out actually is very complicated. You need to use something called second order logic. Okay, so it goes like this. It says, if for all possible, for all possible properties, whatever those are, so for all properties, if it's true that that property holds for 0, and can you make sure that the other Caleb's head's not in the way? If it's true that the property is true for 0,
Just move for now.
and it's true that for all numbers, whenever the property holds for n, that it also holds for the successor of n, then it must hold for all numbers. I'm going to say that again. For any possible property, if that property holds for 0, so in other words, if this fact is true about 0, and if whenever this fact is true about a number, it's also true about the next number, then it must be true of all numbers. Okay, in other words, if you can prove to me that something works for 0, and whenever it's true for a number, it's always true for that number's successor, then since it's true of 0, it must be true of 1. And since it's true of 1, it must be true of 2. And since it's true of 2, it must be true of 3. And this principle of mathematical induction essentially allows you to take the infinite step from it's always true of the next number to just stay flat out, it's true of all numbers. And thus I can prove things that are true about all numbers, and then the monsters become like irrelevant and like disappear in a complicated way, which you can learn about in logic math. All right, this was 20 minutes of either enlightening educational experience or waste of time, depending on how you look at it. All of this was really, for me, to try to convince you that this thing called the principle of mathematical induction, this is not just another little math trick. This is in fact a property which is so basic to numbers that it is built into the very definition of what the numbers are. All right, shall we do a proof? Dawson?
Yes.
Let's do it. And now this might bother you a little bit, because here's what I'm going to prove. I'm going to prove that 1 plus 2 plus 3 plus all the way up to n, that this is n plus 1 over 2. Okay, now, what's probably going to bother you? What's probably going to bother you is, can you raise backward, is that you think that we already proved this, right?
Sort of did.
Yeah, we sort of did. But we didn't, in my opinion, we didn't really prove this. What we did is, we kind of like did some sort of like crap with this, basically. We said, we did this Gauss thing where we kind of said, remember, you know, we do 1 plus 2 plus, and we kind of go all the way up to n, and that's like, we called that s, and then we like wrote them backwards or something, and we said like n plus n minus 1. Remember this?
Yeah.
Of course you do. And then you add them up. Okay, the problem is, there's all these like kind of dots in here, right? So things are sort of like vague. It's unclear what's really going on, and we kind of just said, well, you sort of see how it goes, right? These columns just kind of get added up, and they're sort of all the same, and it just kind of works, and therefore it must be true. All right, so I personally, and okay, it's a sort of a philosophical conversation of what really like a proof is. And if you can convince your audience that it's true, then it's kind of a proof. But mathematical induction enables me to prove it with a sort of a different level of the kind of certainty. All right, so I'm going to show you how this goes. I'm going to pick one that we've already done before because this is just kind of nice to explain what's going on. So what's going on? I want to prove that this is true. And specifically what I want to prove is that it's true for all numbers. All right, so for convenience purposes, I'm going to call this a sub n, and I'm going to call this b sub n. And now this just enables me to do some sort of shorthand, kind of. And what it is that I need to prove now, what I need to prove is that for all numbers n, that a sub n equals b sub n. That's by the way, that's kind of what I mean when I say here's some formula. What I really mean about that formula is this formula is supposed to be true for all numbers, right? So for all n, a sub n equals b sub n. That's what I need to prove. Okay, well, we can do this by induction. And induction works in two steps. There is the base step, or some people call it the base case. In the base case, we have to verify that the formula is true for 0. or for the first number which we're interested in. What's the first number that we're interested in now? 1. So I'll actually write for n greater than or equal to 1. Although I guess it works for 0 too, but it's more exciting to start with 1. Okay, so is the statement a sub 1 equals b sub 1, is that true? Yeah, what is a sub 1? A sub 1 says, start with the first number, start with the number 1, and keep going until you get to n. But n is just 1 in this case, so what's a sub 1? It's just 1. What is b sub 1? Well, b sub n is just a formula which says take the number times 1 plus that, or the number plus 1 over 2, and what is that? That's also 1. And so we have that a sub 1 equals b sub 1, check. Okay, in other words, I've verified that this formula is true for n equals 1. Okay, and now comes the important part, the inductive step. And in the inductive step, my goal of the inductive step is to prove that whenever this formula is true for a number, it's true for the next number. Okay, so what we're going to do is we're going to suppose for some particular k, that a sub k equals b sub k. Okay. Well, ready? Oh, and I suppose we're k has k to be greater than or equal to 1. And then, if I suppose that this is true for a sub k equals b sub k, then what should I do?
In a sub k plus 1.
Yes, and try to prove that a sub k plus 1 equals b sub k plus 1. In other words, what I need to prove is that this property is inherited by the next number.
And you have to use that a sub k equals b sub k.
I have to use that a sub k equals b sub k. Now, this bothers some people because it sounds like we're assuming the thing that we're trying to prove, right? Why is that not true, Mateo? Is that true? Am I assuming the thing that I'm trying to prove?
Oh, I know.
Call on Eleanor because she raised her hand. Eleanor, am I?
No, because you're saying suppose for some particular number, k is greater than or equal to 1, and you've already proved that for 1 it's true. So, like 1, you know that 1.
It's not exactly it. It's not exactly it. Yeah.
Well, what you're saying is that you know it works for this particular case.
Uh-huh.
So what you're trying to prove that it works for all cases.
Yeah. Yeah, the actual theorem, the theorem is that this statement is true for every single number. What I'm assuming is that it's just true for some particular number. That's kind of that's a subtle distinction. I'm supposing it's true for some particular number, and then I'm going to show it's true for the next number. Okay, let's just do it, because it's actually not that hard. So how do I prove that a sub k plus 1 equals b sub k plus 1? Well, it's like some kind of trig identity or something, right? Start with a sub k plus 1. What is a sub k plus 1?
2k plus 1.
Wait, what?
With that a sub n, right?
What? Wait, hold on. What does a sub k plus 1 even mean? What does that mean?
The thing.
It just means 1 plus 2 plus 3 plus, and this time we stop at,
K plus 1.
yeah, we stop at k plus 1. So a sub k plus 1 just means 1 plus 2 plus 3 plus all the way up to k plus k plus 1. Everybody cool with that? Okay, now what?
Well, we already know what the a sub 1 is.
What? No. This is just, what is 1 plus 2 plus 3 plus all the way up to k?
Okay.
That's just a sub k. In other words, a sub k plus 1 is just a sub k plus one extra number, k plus 1. Cool?
Yes.
And now, what do? We use the inductive hypothesis. So now we're going to use the inductive hypothesis. The inductive hypothesis, oh yeah, that's what this is called, the inductive hypothesis. And the inductive hypothesis says that a sub k equals b sub k. So this then equals b sub k plus k plus 1. Is everybody with me? I just did a substitution. I did a substitution, I think the red marker. I did a substitution of a sub k for b sub k, and then, okay, what is the meaning of b sub k? What is the meaning of b sub k?
K times K plus 1.
It is by the formula k plus 1 over 2 plus k plus 1. Did everybody see what I just did? I just substituted in the meaning of b sub k. Okay, now what?
Now you get a common denominator.
Sure, let's factor out, okay, I can do that. So I get k plus 1 plus 2 times k plus 1 over 2.
And then you like factor out the K plus 1.
Factor out the k plus 1. And if I factor out a k plus 1, I get k plus 1 times k plus 2 over 2. Am I still in frame and stuff?
Yeah. Currently.
Okay, and then that's just
And that is just what, Nikili?
B sub K plus 1.
That is, just by the definition of b, this is b sub k plus 1.
Yeah.
Just plug k plus 1 in for n, right? Okay, so what happened is I achieved the thing that I was trying to achieve. What happened is I have this weird formula. I want to see if this weird formula is true or not. I check by brute force that it's true for case n equals 1, and it is. And now I suppose that it's true for some particular number, and then I prove that that formula, if it's true for some particular number, then it's also true for the next number. In other words, you can think of this equation as being a property. This is a property that either a number has or it doesn't have. If this equation is true for a certain number, then it has that property of that this equation is true for that number. And if not, not. What I showed is that 1 has that property of making this equation true, and whenever a number has that property of making this equation true, that property is inherited by the next number. Whenever this equation is true for a number, it's true for the next number. And since it's true for 1, and I proved that whenever it's true for a number, it's true for the next number, it must be true for 2. Can you with me? And since it's true for 2, and whenever it's true for a number, it's true for the next number, it must be true of 3, etc., etc., etc. So, Matteo, it's kind of like common sense sort of says, well, then it must be true for all numbers, right? And that is what the principle of mathematical induction enables me to do. The principle of mathematical induction enables me to conclude that. So now we have this magic sentence. So here's the magic sentence, and I want you to write this every time because it shows that you actually understand what's going on. A sub 1 equals b sub 1. We showed that that's true. And now we just state the conclusion of the inductive step. The conclusion of the inductive step is that for all possible k, a sub k equaling b sub k implies that